Hi everyone, and welcome to the first of 4 videos going through some past exam questions on the topic of neutralisation and acid titration curves. But there's also quite a lot of other questions I wanted to put into this that's just more practice of calculating pH and buffer solutions, because I think that's a topic that definitely a lot of people often struggle with. So in this first question, it's talking to us about this nitrous acid. So it's a weak acid, it's given us the Ka, wants us to write the expression for Ka. Okay, so this is always the same thing. Your Ka is the products of the acid dissociating. So it's always going to produce the proton, and therefore it must be an NO2 minus ion, and then divided by the concentration of the acid itself. And remember, you do need to use the square brackets to represent concentration. Right, it then says calculate the pH of this acid if we know what the concentration is. So this is where we're going to use our Ka expression. It's nice that they've asked us to write it out first, because now we've got it. If we want to calculate the pH, then the thing that we need is the H plus concentration. So we're going to need to rearrange this, but because this is a weak acid, the first thing we want to do is convert our Ka expression into a different form, where we want to say it's H plus squared. Okay. The reason we can do that is because whenever you have a weak acid, when it dissociates, this molecule will split up and produce one H plus ion and also one NO2 minus ion. So the concentrations of these two are always going to be equal to each other if all you've got is a weak acid. So therefore, we can get rid of this from our equation and turn it into H plus squared. Now, we want the H plus concentration if we want the pH, so we need to rearrange this. So we're going to end up with the H plus concentration squared is the Ka times the acid concentration, and therefore the H plus concentration is the square root of that sum. And so therefore the H plus concentration is the square root of the Ka value from here, 4.69 times 10 to the minus 4, times by 0.12. So the H plus concentration is going to be equal to, let's calculate this, so 4.69 times 10 to the minus 4 times 0.12, and then do the square root of that. So our H plus concentration is 7.50 times 10 to the minus 3. And then to get the pH, what we're going to do with this is we want to do the negative log of the H plus concentration. So the pH is the negative log of 7.5 times 10 to the minus 3. So therefore, if we just do the log of that answer, and it gives us minus 2.12. So if we want the negative log, it's just going to be 2.12. So the pH is 2.12. That's the answer that we want. Okay, moving on. The chemist prepares 1 decimeter cubed of a buffer solution by mixing the nitrous acid with sodium nitrite. Okay, so this is the method of making a buffer solution where you've mixed a weak acid with the salt of its conjugate base. So we want to calculate the pH of the buffer solution. Okay, so we're going to start with the Ka again. Okay, all these questions, you want to start off with your Ka expression. But this time, because it's a buffer solution, we cannot say that these two concentrations are going to be equal to each other. Okay, they would be equal to each other if we just had the acid, but we've also got NO2 minus ions coming from the sodium nitrite, and this is not producing any H plus ions. So therefore we're going to have extra of these. So these two concentrations are not going to be equal. So we can't use this H plus squared tactic that we used here. Instead, we're just going to have to rearrange this as it is. We still want to calculate the pH, so we still want the H plus concentration. So it's going to be the Ka times the acid concentration divided by the NO2 minus concentration. Okay, and then we just need to find the values to put in here. We cannot just use the concentrations that we've got here, because these were the concentrations before they were mixed together. We need to work out what the concentration is going to be after we've mixed them together. Okay, so that's our next step. That's how we're going to move forward. So we want to work out the new concentration of the acid. So to do that, we're going to do the concentration times the volume to get the moles, and then do the moles divided by the total volume that we've got now. Okay, so we're going to do 0.2 moles per decimeter cubed times 200 over 1,000, which is the decimeters cubed. So that's going to give us the moles, so it's going to be 0.2 times 0.2. So we've got 0.04 moles. I think it's really important when you're doing these kind of calculations that we write the units on so that we know what we're doing, we don't get lost, and also so it's easy for the examiner to follow. Okay, and now we're going to do the moles divided by the total volume, which is 1 decimeter cubed, isn't it? Okay, because and also we had the 200 from here and the 800 from here. So divided by 1 decimeter cubed. So it's just going to be 0.04 moles per decimeter cubed. So that is our new acid concentration that we can put in here. Now we need to do the same thing for this one. So the new concentration of NO2 minus, we're going to do its concentration that it was to start with times 800 over 1,000. So we're going to have 0.0625 times 0.8, and that's going to give us 0.05 moles, and then again divide it by the volume. It's nice that in this case it just happens to be 1 decimeter cubed, so it's nice and easy, but don't forget, I'm going to write this down anyway because we don't want to forget that we need to do that step. You know, if the volume is anything other than 1 decimeter cubed, then it doesn't matter that we're doing that. Right, so now we have the concentrations, now we can calculate this. So now we can say that our H plus concentration is the Ka value we had earlier on in the question, right back up at the top here, 4.69 times 10 to the minus 4. So we'll go for that. And then we need to make sure we get these the right way round. We want HNO2 on the top, which was 0.04, divided by the other one, which is 0.05. Okay, so that's going to come out as, let's work that out, 4.69 times 10 to the minus 4 times 0.04 divided by 0.05. And we get 3.752 times 10 to the minus 4. And then finally, because we want the pH is going to be the negative log of 3.752 times 10 to the minus 4. So if we just do the log of that answer, minus 3, what do I want, 2 decimal places? Yeah, 2 decimal places. So it'll be minus 3.43, but it's going to be plus 3.43. Okay. Just if you're wondering why don't I type in minus log, just because if you've already done a calculation, if you're not careful, what you end up doing is whatever you've just calculated, take away the log of something. So I never write minus log in my calculator. I always just put log and then take the minus sign off, just to be on the safe side. Right, and then the last bit of this question is a bit more of a wordy one. So it says, explain how this buffer solution controls the pH when a small amount of HCl is added or a small amount of NaOH. So a little bit of acid, a little bit of alkali. Okay, remember this is what a buffer solution does, isn't it? It minimizes pH changes when we add small amounts of acid or alkali. Okay. In your answer, include the equation for the equilibrium. So this is really important. Okay, it doesn't always say this in the question. Okay, and this is the most common thing that I see people getting wrong is they don't write the equilibrium out. Okay. So the first thing, our acid was this HNO2, wasn't it? So the first thing we need to do is write that equilibrium. And then we need to explain what's going on. So when HCl is added, the H plus ions from HCl react with NO2 minus ions. Okay, the H plus ion is going to react with those, and then the equilibrium is going to shift to the left. And then when NaOH is added, the OH minus ions from the NaOH react with, and you could explain this one of two ways. You could say it reacts with the HNO2, or you could say it reacts with the H plus ions. Okay, I'm going to go for that one, but it's fine. You could say it reacts with this. React with the H plus ions to form H2O. Then more HNO2 dissociates to replace the H plus ions. And so therefore the equilibrium is shifted to the right because more of this acid is dissociating. And this is a really nice question because it's consistent, it's always the same. Okay? As long as you write your equilibrium out this way round with the acid dissociating, which is kind of the sensible way to write it, you would write it that way around, then it's always going to be that when you add acid, it shifts the equilibrium to the left, and when you add alkali, it shifts the equilibrium to the right. Okay, so this is kind of a nice sort of formulaic question where whenever you get this question, you're going to approach it in the same way.